Imagine standing on solid ground, feeling the quiet stability of the planet beneath your feet. The mountains seem immovable. The continents appear permanent. Beneath us lies thousands of kilometers of rock and metal that most of humanity rarely thinks about. For most of human history, the deep interior of the Earth was a mystery so vast that it almost seemed unknowable. Ancient civilizations imagined underground worlds filled with fire, mythical creatures, or endless caverns stretching toward the center of the planet. But modern science replaced these myths with something far more precise. Or so we thought. Today, nearly everything we believe about the structure of our planet comes from careful scientific reconstruction. According to this model, Earth is made of several distinct layers. The thin crust forms the surface we live on. Beneath it lies the mantle, a massive region of hot, slowly moving rock extending nearly 3,000 kilometers downward. And at the very center lies the core. The core itself is divided into two parts: an outer core made of molten liquid metal, and an inner core that is solid, despite temperatures that rival the surface of the sun. For decades, this layered structure appeared well understood. But deep beneath the surface, something unexpected was happening. And scientists only began to notice it recently. The strange story begins not in the depths of the Earth, but on its surface, during earthquakes. When a powerful earthquake strikes somewhere on the planet, enormous amounts of energy are released into the surrounding rock. This energy travels outward in waves, rippling through the Earth much like sound travels through air. These seismic waves move through the planet's interior, passing through layers of rock, magma, and metal before eventually reaching sensitive detectors known as seismometers. Thousands of these instruments are scattered across the globe. Together, they form one of the most powerful scientific networks ever built. By measuring the precise arrival times of seismic waves, scientists can determine how fast the waves traveled and what materials they passed through along the way. This method allows researchers to reconstruct an invisible map of Earth's interior. In many ways, it works like a medical CT scan. Doctors use X-rays passing through the human body to reconstruct an image of organs and bones. Seismologists use earthquake waves passing through the Earth to reveal what lies thousands of kilometers beneath the surface. Over time, this technique revealed something extraordinary. The Earth's core was not simply a molten ocean of metal. Instead, it had structure. In the early 20th century, scientists discovered that seismic waves behaved strangely when they approached the center of the planet. Certain types of waves would disappear entirely, while others bent in unexpected ways. These observations led to one of the most important discoveries in geophysics. The outer core must be liquid. Liquid metal prevents certain seismic waves from passing through it, creating a shadow zone where detectors on the other side of the planet receive no signal at all. But the surprises did not stop there. In 1936, Danish seismologist Inge Lehmann noticed something peculiar in the seismic data from distant earthquakes. Some waves were arriving at stations where they theoretically should not exist. This meant that something inside the core was reflecting them back. Lehmann realized the only explanation was that Earth contained an inner solid core sitting inside the liquid outer core, like a metal sphere suspended within a vast ocean of molten iron. It was a revolutionary discovery. For the first time, scientists had evidence that the center of our planet was not entirely liquid, but contained a solid heart. And for many decades, this model appeared to explain everything. But science rarely stands still. As seismic technology improved, researchers began to collect more precise data than ever before. Global networks of digital seismometers could now record earthquakes with incredible accuracy. Earthquakes in one part of the world could be studied from thousands of kilometers away. And when scientists began comparing seismic signals from earthquakes separated by many years, they noticed something unexpected. Something deep inside the Earth appeared to be changing. At first, the differences were extremely subtle. Seismic waves traveling through the core would arrive just fractions of a second earlier or later than predicted. The variations were so small that many researchers initially assumed they were measurement errors. But the anomalies kept appearing. Again and again. The deeper scientists looked into the data, the more puzzling the patterns became. Certain waves passing through the inner core seemed to change speed over time. And these changes were not random. They appeared to follow a pattern. A pattern suggesting that the inner core itself might be moving differently than the rest of the planet. This idea was startling. For decades, the inner core had been assumed to rotate in perfect synchrony with the Earth's mantle and crust above it. But what if it didn't? What if the very center of our planet had its own motion, separate from the surface world we inhabit? If this were true, it would mean that Earth's interior was far more dynamic than previously imagined. And if the inner core could change its behavior over time, it could alter how heat flows through the planet, potentially affecting everything from the magnetic field to the stability of tectonic plates. In other words, the deepest part of the Earth might be quietly shaping the entire planet in ways we are only beginning to understand. Scientists began to reanalyze decades of seismic data, comparing earthquake records from the same locations across many years. And as the evidence accumulated, one conclusion became increasingly difficult to ignore. Something inside Earth's core was shifting. But the deeper researchers looked, the more complicated the story became. Because the data was hinting at something even more surprising, something that challenged one of the most fundamental assumptions about the planet's interior. The inner core might not only move differently from the rest of the Earth. It might even change the direction of its motion over time. And if that was true, it meant that the center of our planet was not simply a solid metal sphere quietly sitting beneath our feet. Instead, it might be a dynamic, evolving world hidden thousands of kilometers below the surface. A world whose behavior could reshape our understanding of Earth itself. And what scientists would discover next would reveal that the very heart of our planet may be far stranger than anyone ever imagined. And what scientists would discover next would reveal that the very heart of our planet may be far stranger than anyone ever imagined. For decades, the inner core was assumed to be a simple structure, a dense, solid sphere of iron and nickel quietly sitting at the center of the Earth. Locked in place by immense pressure, it was believed to rotate in perfect harmony with the rest of the planet. But seismic evidence was beginning to suggest something very different. In the 1990s, researchers studying earthquake data noticed subtle timing differences in seismic waves traveling through the inner core. These waves, known as kick waves, pass directly through the center of the Earth before emerging on the other side of the planet. Because these waves travel through the deepest region of the planet, even the smallest variations in their travel time can reveal important details about the structure and movement of the inner core. When scientists compared waves from earthquakes occurring years apart but traveling along nearly identical paths through the planet, they noticed something puzzling. The waves were arriving at slightly different times. Not minutes apart. Not even seconds. But fractions of a second, sometimes just tenths or hundredths of a second. At first glance, such tiny variations might seem insignificant. But to seismologists, these discrepancies suggested that something deep inside the Earth had changed. Imagine sending a pulse of sound through a solid metal sphere. If the sphere remains perfectly still and unchanged, the sound should always travel through it at exactly the same speed. But if the sphere rotates or shifts internally, the path through the metal changes, and the sound arrives slightly earlier or later. That is precisely what the seismic data seemed to show. The inner core appeared to be rotating at a slightly different rate than the rest of the planet. Scientists began referring to this phenomenon as superrotation. According to this theory, the inner core was rotating slightly faster than Earth's surface, completing an additional rotation every few hundred years. It was a subtle difference, but its implications were enormous. If the inner core was moving independently, it meant that powerful forces deep within the planet were driving its motion. These forces likely came from the outer core, a vast ocean of molten iron and nickel surrounding the solid inner core. The outer core is constantly in motion. As heat escapes from the deeper parts of the planet, hot metal rises while cooler metal sinks. This circulation creates massive electrical currents within the liquid metal, and those electrical currents generate Earth's magnetic field. The magnetic field acts like a protective shield around the planet, deflecting harmful solar radiation and preventing our atmosphere from being stripped away by the solar wind. Without it, life on Earth would be dramatically different. So the movement of the outer core is already critical to the survival of the planet. But if this swirling ocean of molten metal interacts with the inner core, it could exert enormous forces on the solid sphere at the center of the Earth. These forces could cause the inner core to rotate slightly faster than the mantle and crust above it. At least, that was the initial interpretation. For years, the idea of inner core superrotation became widely accepted among geophysicists. But as more seismic data accumulated, the story began to change. Scientists began analyzing earthquake records spanning several decades, some dating back to the 1960s. Instead of examining individual earthquakes, researchers compared repeating earthquakes, events that occur in nearly the same location and produce almost identical seismic waves. These repeating signals act like natural experiments. If the path through the Earth remains unchanged, the seismic waves should arrive at exactly the same time each time an earthquake occurs. But researchers began noticing something strange. The timing differences were not consistent. In some years, the waves suggested that the inner core was rotating slightly faster than the surface. In other years, the timing shifts appeared to slow down. And eventually, some data suggested the motion might even be reversing. This possibility was astonishing. It implied that the inner core might not rotate steadily at all. Instead, it might oscillate, gradually speeding up, slowing down, and possibly even reversing direction relative to the mantle above it. In other words, the center of the Earth might behave like a massive mechanical system slowly shifting over decades. To test this idea, scientists from several research institutions conducted a large-scale analysis of seismic data recorded over more than 50 years. They focused on earthquake waves passing repeatedly through the inner core between specific pairs of locations, particularly between South America and Southeast Asia. By studying how these waves changed over time, they were able to track the motion of the inner core with remarkable precision. And what they found surprised the scientific community. The data suggested that the inner core's rotation had been gradually slowing down. By the early 2000s, the motion appeared to nearly stop relative to the Earth's mantle. And in recent years, some measurements suggested the rotation might even have begun moving slightly in the opposite direction. This discovery hinted at a slow, decades-long cycle occurring deep within the Earth. A cycle where the inner core speeds up, slows down, and then reverses relative to the outer layers of the planet. Scientists now believe this oscillation may occur roughly every 60 to 70 years. But why would the inner core behave this way? The answer may lie in the complex interaction between two enormous forces deep within the planet. On one side, the swirling currents of molten iron in the outer core generate powerful magnetic forces that pull the inner core forward. On the other side, the solid mantle surrounding the core exerts gravitational forces that try to keep the inner core aligned with the rest of the planet. These two forces are constantly competing. Sometimes the magnetic forces dominate, causing the inner core to rotate slightly faster. Other times, gravitational forces slow it down. The result may be a delicate balance that causes the inner core to oscillate back and forth over time. But as researchers examined the seismic data more closely, another mystery began to emerge. The inner core might not only be changing how it rotates. Its internal structure might also be evolving. Some seismic waves traveling through the inner core move faster in certain directions than others. This suggests that the iron crystals inside the core are aligned in specific patterns. And those patterns may shift over time as the core slowly deforms under extreme pressure. In other words, the center of our planet might not be a perfectly rigid sphere at all. It could be slowly reshaping itself, changing structure, changing motion, possibly even affecting the behavior of the magnetic field that protects our entire world. But the deeper scientists investigated these possibilities, the more extraordinary the implications became. Because if the inner core truly moves in cycles, and if those cycles influence Earth's magnetic field, then the hidden rhythms of the planet's center might affect processes occurring all the way up at the surface. Processes that shape our environment, our climate, and the stability of the magnetic shield surrounding the Earth. And that realization was leading researchers toward an even more profound question. What if the slow heartbeat of Earth's inner core is part of a much larger planetary system, one that humanity is only beginning to understand. What if the slow heartbeat of Earth's inner core is part of a much larger planetary system, one that humanity is only beginning to understand? To appreciate the significance of this possibility, we need to step back and consider the incredible scale of what is happening beneath our feet. Nearly 5,000 kilometers below the surface of the Earth, at pressures more than 3 million times greater than atmospheric pressure and temperatures approaching 5,500 degrees Celsius, lies a sphere of metal roughly the size of the Moon. This is the inner core. It is composed primarily of iron and nickel, compressed into a solid state by pressures so immense that even temperatures comparable to the surface of the Sun cannot melt it. Surrounding this solid sphere is the outer core, a vast ocean of molten metal in constant motion. Together, these two layers form one of the most powerful engines operating within our planet. The churning flow of liquid iron in the outer core generates Earth's magnetic field through a process known as the geodynamo. As electrically conductive metal moves through the core, it produces electrical currents. These currents generate magnetic fields, which in turn influence the motion of the liquid metal. The result is a self-sustaining magnetic engine deep within the Earth. This invisible field extends tens of thousands of kilometers into space, forming a protective bubble known as the magnetosphere. Without it, charged particles from the Sun would continuously bombard our atmosphere, gradually stripping it away, a fate that may have happened to Mars billions of years ago. In this way, the processes occurring at the center of the Earth help protect the entire planet. But if the inner core is indeed shifting its rotation over decades, then the balance of forces inside this geodynamo may also change. Scientists are now investigating whether subtle variations in the inner core's movement could influence fluctuations in Earth's magnetic field. And interestingly, the magnetic field itself is known to behave in surprisingly complex ways. For centuries, navigators have relied on the magnetic North Pole as a stable reference point for navigation. But careful measurements have revealed that the magnetic poles do not remain fixed. Instead, they wander slowly across the surface of the planet. In recent decades, the magnetic North Pole has been drifting across the Arctic at an unusually rapid pace, moving from northern Canada toward Siberia. At the same time, satellites have detected regions where the magnetic field has weakened significantly, particularly over the South Atlantic Ocean. This region, known as the South Atlantic Anomaly, represents an area where Earth's magnetic shield is temporarily weaker than elsewhere on the planet. Spacecraft passing through this region often experience increased radiation exposure. While these magnetic variations are not dangerous to life on Earth, they reveal that the magnetic field is constantly evolving. And deep within the planet, the movement of the core may play a crucial role in shaping those changes. But the implications of inner core dynamics may extend even further. Some researchers have begun to investigate whether long-term cycles in the inner core could subtly influence processes occurring in the mantle above it. The mantle is not a rigid shell. Instead, it slowly flows over geological timescales, driven by heat rising from the deeper layers of the Earth. These slow convective currents in the mantle drive plate tectonics, the movement of continents across the planet's surface. Over millions of years, tectonic forces reshape the geography of the Earth. Mountains rise. Oceans open and close. Entire continents collide and break apart. While these processes unfold on timescales far longer than human history, they are ultimately powered by the heat flowing outward from the Earth's interior. And that heat originates, in large part, from the core. If the inner core's motion influences how heat flows through the outer core, it could potentially alter the energy transferred into the mantle above. In other words, the deep rhythms of Earth's center might help regulate the slow geological processes that shape the surface world. For now, these ideas remain active areas of research. The interior of the Earth is incredibly difficult to study directly. Unlike the surface of Mars or the icy moons of Jupiter, we cannot send spacecraft to explore the core. Instead, scientists must rely on indirect evidence, seismic waves, magnetic measurements, laboratory experiments, and advanced computer simulations. In recent years, powerful supercomputers have allowed researchers to simulate the extreme conditions inside Earth's core with unprecedented detail. These simulations reveal a complex, dynamic environment where heat, magnetism, and fluid motion interact in ways that are still not fully understood. Some models suggest that the inner core may not be perfectly uniform. Instead, it might contain multiple layers or regions with different crystal structures. Some studies even propose the existence of an innermost inner core, a region at the very center of the planet where iron crystals may be aligned in a completely different orientation. If this is true, it would mean that the Earth's core is even more complex than scientists previously imagined. A layered structure within a layered structure. A world hidden beneath thousands of kilometers of rock and metal. And yet, despite all we have learned, the center of our planet remains one of the least explored places in the solar system. No probe has ever reached it. No camera has ever seen it. Everything we know about the core comes from interpreting faint signals traveling through the Earth. Tiny vibrations generated by earthquakes. Ripples of energy carrying clues from the deepest regions of the planet. And those clues are telling us that the Earth is not a static world. It is a living system, dynamic, evolving, and interconnected from the deepest core to the highest atmosphere. The discovery that the inner core may shift its rotation over time is more than a technical detail in geophysics. It is a reminder that even the most fundamental parts of our planet can still surprise us. For centuries, humanity believed the Earth's interior was simple and predictable. But each new generation of scientific tools reveals deeper layers of complexity. The deeper researchers look, the more the planet reveals hidden processes shaping the world we inhabit. And somewhere far beneath the continents and oceans, beyond the reach of any drill or machine, the solid metal heart of our planet continues its slow and mysterious motion, quietly influencing the forces that shape the Earth itself. A reminder that even beneath our most familiar ground, the greatest discoveries may still lie hidden.